AI. I'm talking about an absolute giant, a model with over 10 billion parameters. I mean, think about that. That's like trying to cram 10 billion different facts into a single brain. It's, without a doubt, one of the biggest hurdles in tech right now.
So that's the big question, right? How in the world do you actually do that? How do you train a model that massive to understand something as incredibly complex as, say, a video?
Well, the short answer might actually surprise you. On a single, powerful computer, you just can't. It's impossible. Even the beefiest machine you can imagine will just choke. The model is way too big to even fit into its memory.
Let's put this into perspective. You take a brand new, top-of-the-line H100 GPU, the workhorse of the entire AI industry, and you try to load up this 10 billion parameter model. What happens? You immediately hit a brick wall. It's an error. Stands for out of memory. Game over. So, what's the workaround? How do you get past this massive roadblock?
All right, so let's get into the nitty-gritty of this billion parameter problem. Before we jump to the solution, we really need to understand what we're up against. And we're going to use a perfect real-world example, teaching an AI to understand what's happening in a video. Okay, imagine you want a computer to watch a movie and actually get it. You can't just play the file, right? No, you have to break it down. First, you pull out the individual frames. Then, you use a big AI to analyze those frames to figure out the key features. And finally, another AI model has to look for when those features change, so it can tell where one scene ends and the next one begins. Now, this is super important for things like video search or even automated content moderation. But that middle step, analyzing the frames, that's where our 10 billion parameter giant is supposed to work. And that's exactly where everything grinds to a halt.
So, if one computer can't do it, what's the answer? Well, you use a whole bunch of them working together. This whole concept is called parallelism, and it's basically a divide and conquer strategy. You take one ridiculously huge job and you chop it up into smaller, manageable pieces that can all be tackled at the same time.
Okay, let's break this down. The first and maybe simplest way to do this is something called data parallelism. The analogy here is perfect. Imagine the AI model is a blueprint for a house. Instead of having one construction crew build one house, you give the exact same blueprint to, say, 8 different crews, and each crew builds an identical house just on a different piece of land. With our AI, this means each GPU gets a full copy of the model, but each one gets a different chunk of the video data to work on.
But what if the blueprint itself is too big for any single crew to even hold? That's our actual problem, right? The model's too big. So that's where tensor parallelism comes in. Here, instead of splitting up the data, we split up the model itself. So sticking with the house analogy, one crew works on the plumbing, another does the electrical, a third does the framing, all at the same time on the same floor of the same house. For our AI, this means one GPU might be processing the colors in a frame, while another is working on identifying shapes. They all have to coordinate perfectly on every single bit of data.
And then there's a third method, pipeline parallelism. The best way to think about this one is like an assembly line. You see, our AI model is built in layers, kind of like a building has different floors. With this approach, the first set of GPUs works on the first layer, the ground floor, and then passes its work up to the next set of GPUs, which handles the second layer, and so on. The data just flows right through this assembly line, getting processed at each stage. Okay, so we've got 3 different ways to slice up this massive problem. So, what if we just did all 3 at the same time? Well, that's exactly the idea behind what's called 3D parallelism. You're splitting the work by data, by model layer, and by the tiny calculations inside each layer. It's like having multiple, specialized assembly lines all working on different houses at once. It's insanely powerful, but you can probably guess it's a logistical nightmare. I mean, how do you even begin to coordinate that kind of chaos?
Well, for an orchestra this complicated, you need a conductor.
You need a piece of software that's brilliant enough to manage all this complexity. And in the world of massive scale AI, that conductor has a name. It's a library from Microsoft called DeepSpeed.
DeepSpeed has this absolutely brilliant strategy called ZRO. That stands for Zero Redundancy Optimizer, and it's all about one thing: eliminating waste. So instead of every GPU holding on to a full copy of everything, DeepSpeed just shatters it all into pieces. And it don't just mean the model itself. It also shards all the temporary data needed for training, things called optimizer states, which are kind of like the model's short-term memory, and gradients, which are the instructions on how to improve. It's basically a hyper-efficient project manager that makes sure no one has duplicate information and everyone gets exactly what they need the instant they need it. And the result of this is just, wow. Look at this. Let's say our huge model needs 10 gigabytes of memory. Normally, every single GPU would need all 10 gigs. But with DeepSpeed's 0-3 strategy, it slices that up across 8 GPUs. So now each GPU only needs to handle 1.25 gigabytes. That's a massive, massive reduction in the memory needed on any single chip. So let's just pull this all together. DeepSpeed is the master conductor here. It takes our giant model, uses that 3D parallelism we talked about, a mix of all 3 strategies, and just seamlessly spreads the workload across 8 powerful H100s. It's this beautiful symphony of hardware and software working together to do something that one machine, on its own, could never ever do. Okay, so that's the theory. It all sounds great, right? But did all this crazy complex engineering actually work? Let's check out the results. Remember that big, scary, out-of-memory error from the beginning? The one that stopped us dead in our tracks? Well, with DeepSpeed conducting the orchestra of 8 GPUs, problem solved. Gone. And not only did the training actually run, it ran with some seriously impressive performance. And we can put a number on that success. The system was able to chew through 67.2 video samples every single second. That's the kind of speed, the kind of throughput you absolutely need if you want to train on massive web-scale datasets.
Okay, now this is the part that's just wild. Logically, if you use 8 GPUs, you'd expect to get, at best, an 8x speedup, right? Well, check this out. The actual speedup they achieved was 8.4x. It was faster than theory said it should be. The system was so good at hiding the communication lag between the GPUs that it beat the theoretical max. That's something called superlinear speedup, and it is pretty much the holy grail when you're doing this kind of work.
And here it is, the final proof. Each of those H100s has 80 gigabytes of really fast memory, and our monster 10 billion parameter model? It ended up using just a tiny 11.2 gigs on each one. There was tons of headroom left. That memory wall we talked about, it wasn't just broken, it was completely demolished. So, we've just walked through how it's actually possible to train a 10 billion parameter AI. It's an incredible piece of engineering, for sure. But what does it all mean? For the big picture. What does this really unlock for the future of AI?
Well, what it means is that the memory wall, that hard limit that used to dictate how big our AI models could be, has been shattered. This whole technique gives us a clear blueprint for how to train the next generation of AI. We're talking about models that are going to be even bigger, way more powerful, and able to understand the most complex stuff out there, especially video.
And really, it's these kinds of breakthroughs, deep down in the infrastructure of AI, that make all the cool tools we're starting to use every day even possible. When you get a really smooth, seamless answer from a service like Perplexity, you can be sure it's standing on the shoulders of incredibly complex engineering just like this.
And that kind of brings us to one last big question to think about. We've cracked the engineering problem. We now know how to build and train these AI giants. So the only real question left is, what do we want